Okay. Well, Jared, Haley, my sincere apologies. Anyone else? I forgot to turn on my microphone. So let's do a quick backup here. We are attempting to graph a cycloid. Cycloid happens when you roll a circle. If you track the point and consider the angle that's swept out here, you get this stuff. Ta-da. Okay. I have another video on my YouTube playlist that goes over this in much more detail from some previous year. But those are the equations I need for a parameterization of a cycloid. All right, so now we're going to try and graph it. Let's see, where was I? Oh yeah, we started with the circle facing down, so the point is right there. We just determined the circumference of a circle is 2 pi. As it rolls once, then along the ground it completely covers 2 pi. So I need to consider t going from 0 to 2 pi, and that's the distance along the x-axis too. So let's just say what? Let's let this right here be pi. Actually, pi is 3.14, right? So if that's 1, 2, 3, 4, 5, 6, that's 7. So right around here is 2 pi-ish, and right around there is about pi. And I'll go the same scale this way, so my circle is 2 units tall. So one thing I know is if the circle spins half a rotation, that point will be at the top at pi. So right over here, that thing should peak. Okay. Before that, let's see, if it just rolls a little bit, like pi over, let's see, pi over 3 is about 1. Right, is that what I want? Yeah. That puts the center about here, and the radius is at pi over 3, which would be out this way. So at pi over 3, I think I'm going to get a point right about there. So we should find that this thing is steeper on the side and then shallower on the top. Now to get some other points, we should kind of plug in some numbers and see what happens. So we're going to need a calculator to get some approximations for x and y and t. So let's just double check if I put pi over 3 in roughly the right spot. Whip out a calculator. So we need pi over 3 minus the sine of pi over 3. If somebody could get a calculator and help double check, that would be awesome. So pi over 3 minus the sine of pi over 3. And Google says the x value should be about 0.2-ish. And my point's a little bit farther to the right than it should be, but I tried. All right, and then if I check what is 1 minus the cosine of pi over 3, I get about 0.5. Beautiful. Let's see, where's my picture over here? And yeah, so I'm a little high and a little too far over there. So my first point, if x is pi over 3, should have been more like over here. Well, and I kind of hit that. This pen's kind of tough to draw with. At, let's see, pi over 2, where would we be? And now I'm wishing I had a spreadsheet. At pi over 2, my y value is 1. And my x value is going to be a little trickier because it's got pi over 2 hanging out there. Cosine of pi over 2 is 0, so it's just pi over 2, right? Yeah, so about 1.6 and 1 when we're pi over 2 units through our revolution. So let's see, 1.6, and ooh, I don't know, is that right? Oh, wait a minute. Oh, it's 0.5. Yeah, sorry. Yeah, sine of, okay, yeah, I did that totally wrong. I should actually calculate it. So it's about 0.5-ish. That's more like it in 1. Okay, and that's about right on track where I was thinking it would be on my graph there. Yeah. And now it's going to behave the same way as it comes down the other side. So there'll be similar points on the other side. So 0.2 back from 2 pi will be at about 1/2. So that's going to be maybe right here-ish. And then about 0.6 back from 2 pi, we're going to be at about 1. So let's see, that's probably going to be about right there. So there is my best cycloid with 1, 2, 3, 4, 5, 6 points. Could plot another one in between, like 3 pi over 4 is going to be somewhere near that top vicinity there. So let me fill in a couple more here. So let's see, what did we have? We had 0.2 and 0.5. And then we did pi over 2, and pi over 2 was 0.6 and 1. And let's try 3 pi over 4 next. Let's see what we get. (1.6-ish) for x. And 1.7-ish for y. Now let's see. 1.6 to 1.7. Yeah, I'm still doing pretty good. Not bad. Okay. Now just some questions to double check. Well, what kind of shape is this? Is this part of an ellipse? Is it part of a circle? Well, if it's a circle, then it should have a constant radius, right? But the center would be around right here. It's 2 units that way, but it's pi units left and right. So it's definitely not a circle, right? Well, could it be an ellipse? I mean, why are we calling it a cycloid? Maybe it's something we already know. If it was an ellipse, anybody remember the equation for an ellipse? It's kind of like the equation for a circle. So we're going to deal with this soon anyway, so we might as well bring it up. It's with a circle, you have x minus some center x value squared plus y minus some center y value squared equals your radius squared. With an ellipse, we put a 1 on the end, and then we divide by these numbers that we usually call a squared and b squared. And they represent the distance out on the horizontal and vertical axis. So for example, here the center would be the point HK, and then the distance from the center to this point over here, that would be a distance of A. Distance from the center to the top, that would be a distance B. All right, so just for fun, I'm going to graph an ellipse to see how it matches up with the cycloid in GeoGebra. I'm not going to do it by hand. That's too tedious. But this is an ellipse. And we will do an ellipse in just a minute. Let's see, where is, here we go. All right, let's go into Desmos, actually. Pretty good job of graphing. So let's see, to do parametric, I set up a point, and then I have to just use t. So I want t minus the sine of t, comma, and we don't want to make t a slider. That kind of messes things up. And then we want 1 minus the cosine of t. And then close parentheses. And it says, hey, let's let t go to 1. And we can say, no, let's let t go to 2 pi. And then it will graph a complete version of it. If I make it go out to 4 pi, it'll give me 2 revolutions of the circle. So I can see more of it evolving there. Now I just want to compare this to an ellipse just to see what they're like. So if I use that equation for an ellipse I mentioned here, based on the picture I drew on the previous page, I would say the center would be pi 0, right? If this is the top half of an ellipse, and then my A would be pi, That's the horizontal distance from the center. And my b would be 2, the distance from the center to the top. So I'm going to type that in and see what happens just for fun to show that this is a new unique curve. It is not part of a circle or part of an ellipse, but it was built by a circle, which is kind of cool. So parentheses x minus pi squared divided by, and let's see, horizontally, I want a pi squared. Ooh, that's cool. Now it's a piece of a parabola. Oh yeah, could that be a piece of a parabola? We could graph an upside down parabola there to check. Plus y minus 0. I guess I don't need a minus 0, do I? Y squared. Y squared divided by 2 squared, or 4, and equals 1. You can see that they don't quite match up. The curvature is a bit different for an ellipse than a cycloid. It's a totally different arc. And I mentioned the other day, it solved a problem a long time ago. And considering if we flip the cycloid, so let's see, if I wanted to flip the cycloid, I would take the opposite of the y values. So if I go minus and plus, I can get the upside down of my cycloid here. If I wanted to know what's the fastest way to roll an object from this point here to, say, this point right there, the cycloid is the fastest way to get there. Not a straight line, not a piece of a circle, not a piece of an exponential, not a piece of a parabola or an ellipse or any other curve you can imagine. It turns out we can justify that the cycloid is the best curve for that job. The other thing it satisfies, if we want to get a point from, let's say, anywhere up here down to the bottom, it takes exactly the same time whether I start the ball here or there to get to the bottom, which is another crazy property of this curve. Okay, and what's that? We are neglecting friction in that, yes. Yeah, all we have is gravity pulling down, and the curve is just in the way of that. Am I telling the truth or am I lying there? I'm pretty sure I'm telling the truth that we're ignoring friction there. Well, it would just slide. Yeah. Okay, I got to get back to you on that. I will think about that some more and do some research. But I'm pretty sure we're ignoring friction, in which case the ball would be sliding. You are correct. It would not roll. Yeah. Okay. So the problem of what's the fastest way to get from here to here, that's called the Brachistochrone problem. And the problem of what's the same time from anywhere to there, that's called the Tautochrone problem. And people were looking to solve them for different reasons. One of them was when they were building clocks. It turned out this was an important thing for building clocks a long time ago when they're trying to make an accurate clock. Anybody know why we needed an accurate clock? We had latitude down pretty good, but longitude was a problem when traveling across the sea. And the only way to try to be accurate about where you were was by having an accurate clock that allowed them to better predict what one's longitude was, which is kind of cool. So, all right, so that's the cycloid. So let's play with the cycloid now. Just to note, because of the way we derive the shape of the cycloid with this rolling circle, and because of the way arc length is related to the angle that's swept out, if you use a bigger circle or a smaller circle, you just multiply everything by r, whatever the radius of the circle is. So we can do any radius we want. So for example, let's play with a circle of radius 2. So the equation of that cycloid would just be x equals 2 theta minus 2 sine theta, and y equals 2 times 1 minus 2 times cosine of theta. And so one thing you're going to want to have over the next several days is a calculator that can do parametric equations. Most calculators can. The Desmos app can do it. If you have a TI, you just have to switch to parametric mode. Other things to consider when we graph something that's parametric, we not only have X and Y to consider, what's the min, what's the max, but we also have to see is what should T start at and what should T end at. So those are all things to consider. So if you're using a TI in your window, you'll have to set boundaries for T, because the TI uses T instead of theta, and X and Y. So I'm just going to graph that sucker in Desmos, and then we'll ask a few questions about it. So let's see, starting up Desmos. Let's get rid of the ellipse and put this back in its regular orientation. And we're going to double everything. Okay, so then I'm going to have to zoom a little bit. And so let's see. The other thing to think about in terms of it rolling, the bottom line is theta is our angle here, and 1 revolution is 2 pi. So no matter how big the circle is that rolls, it still makes 1 revolution from 0 to 2 pi. So T doesn't change anything. R just means it is a bigger cycloid, but it still happens from 0 to 2 pi. Okay. Okay, so that's my new cycloid there. Let's see. I think I can plot a point here. It's if I let A equal pi over, let's see, pi over 4 is a cute number. I want to see the point 2A minus 2 sine of A, comma, 2 minus cosine of A. I'm going to plot a point on this curve. Did I make it work? Oh, I missed my 2 there. Yeah, thank you. There we go. All right. I want to do one higher up. Let's go pi over 4, 3. Let's go pi over 2. Okay. What we're going to do is we're going to attempt to find a tangent line at that point. Okay. So let's do it. And I want a different color in a minute. So we are going to find a tangent line at theta equals pi over 2. So some things we need to know is we need to know what point is that there. And I had GeoGebra graph it for me, but I should calculate it here too. X is going to be 2 times pi over 2, which is pi. And then the sine of pi over 2 is 1. So it's pi minus 2, or approximately 1.14-ish. And then y is going to be 2 minus the cosine of pi over 2, which is 0, right? Yeah. And so I just get 2. So on GeoGebra, that graph should look like about 1, 2-ish. 1, 2-ish. Yep, that looks about right. Okay. Next, how to find the slope. Well, slope, so I have a point, right? New color, come on, colors, get back here. We are. Oops. All right. Slope, well, we have a definition for that. It is the instantaneous rate of change dy dx. But I don't have y as a function of x here. What I do have is y as a function of theta and x as a function of theta. And it turns out, fiddling with differentials, which is sometimes dangerous, but often not, we can look at dy dt, rate of change of y with respect to time, divided by the rate of change of x with respect to time. And that'll still give us the slope. keep in mind, once we get into parametric equations, we have some parameter that's moving x and y. So speed is totally different. We'll take a look at speed in a minute. Slope and speed are not the same thing. Slope is just the tilt at some point. Speed is something else based on this new parameter. Okay, so let's find dy dt and dx dt and put them together. So, new page. The derivative of y with respect to t, well, the derivative of 2 is 0, and the derivative of the cosine is the negative sign. So I think we end up with 2 times the sine of, theta, not t. What did I write back here? I put t's there too, oops. It's a good thing theta starts with t. Okay, sine of theta. And then dx d theta, derivative of 2 theta is 2, minus 2 derivative of sine is cosine of theta. And so putting both of those together, we get that dy dx is, oh, the 2's factor out, that's kind of nice. It is the sine of theta divided by 1 minus cosine of theta. And that looks like a trig identity I've seen before. Huh. Can't quite bring it to mind though. All right, and then what we want to do is we want to evaluate that derivative when theta is equal to pi over 2. So let's see, sine at pi over 2 is 1. Cosine is 0, so I get a slope of 1 there. So I'm going to put all that together. Let's see, what do we have back here? We have x is pi minus 2 and y is 2. So I'm going to use the point slope form. Point slope form says take a y minus the y value, and that's equal to your slope times x minus your x value. And so if I subtract pi minus 2, it's going to give me a negative minus pi plus 2. Cleaning that up, adding the 2 to the other side, it looks like we get y equals x minus pi plus 4. So the y-intercept is about, what, 0.8-ish. Let's give it a try, see how it looks. And we could do a parametric line, but I see no reason to do that here. So y equals x minus pi plus 4. And that looks pretty darn good. Nice. Okay. What else fun could we do? Wouldn't it be nice to find the arc length of this sucker? Oh, question? Oh, speed. Yeah. Let's talk about speed. Okay. Speed is trickier. Okay. And I'm just going to do the short version of speed here. So parametric speed. So normally we talk about slope. We've got these 2 points, right? And we make our little triangle and we go from one point to the other, and that's how we get our slope. This is, say, delta x right there, and this is delta y right there, okay? The length of this curve, according to the Pythagorean theorem, because that's a right triangle, is the square root of delta y squared plus delta x squared. Agreed? Okay. Now, speed, well, that's just your total distance divided by your total time. Well, as we traveled a little x ways and a little y ways, that means t had to move a little to make that happen. So to get from this point to that point, there had to be some change in time. So it turns out once we have this parameter that forces x and y to do stuff, then distance ends up being, that's our distance right there, right? We went from one point to another. So it's that square root of delta y squared plus delta x squared. And our time happened to be that little bitty change in time. Cleaning that up a little bit, I could say that delta t, new color please, could be considered to be the square root of delta t squared. Putting this together with that in the division, then I could consider my speed to be delta y squared plus delta x squared all over delta t squared. Because everything's positive here, I can put it all together. Since both of these are divided by delta t squared, then I can rewrite this one more time and say, hey, what I really have here is delta y over delta t squared plus delta x over delta t squared, all squared, inside the square root. And if we take the limit as delta t goes to 0, what we get is the derivative of y with respect to t here and the derivative of x with respect to t there. So because we have this extra parameter moving along x and y, it dictates the speed. And so speed with parameters is always achieved with the Pythagorean theorem, dy dt squared plus dx dt squared, all inside the square root. So if we wanted to know how fast the point was moving at that particular instant, it's not the slope, it's the parameter that determines that. So let's see, let's check that for our instance. We're using thetas instead. We had theta equals pi over 2. And let's see, what was our that's 2 sine and then 2 minus 2 cosine. All right. So we've got twice the sine. Everything's squared. Oops. Plus 2 minus 2 cosine, I believe it was, squared, all inside the square root. Now here, it probably makes more sense to plug in the pi over 2 and then clean this mess up. Okay. So let's see, if I plug in the pi over 2, sine at pi over 2 is 1. So that's going to give me 2 squared, which is 4. Cosine at pi over 2 is 0, so I get another 2 squared, or 4. So I have the square root of 8, which is twice the square root of 2. See, square root of 2 is about 1.7, so this is like 3.4-ish units per second. And what we'll find is that that point's going to be moving at different speeds at different times as the circle rolls at a constant speed. Okay, the point is going to be having a slightly different speed because of the angle that's going around there with it, which is kind of wild. We're going to come back to this in just a minute. There's other kinds of cycloids out there, depending on where you put the point. Now we put the point on the edge of the circle. What if the point was inside of the circle or outside of the circle? Now, inside of the circle, I can think of a visual example of that, a reflector on a bicycle wheel. That is a point revolving around in a circle. It's not on the edge, so you're not going to quite get a cycloid, but it's something close to that. And my recollection is that's called a prolate cycloid. Prolate cycloid, is that right? I think so. And I think Wolfram alpha had some, oh, there's a curate cycloid too. Let's check out prolate first, because that's the one that came into my head first. Okay, so there they have a point outside rolling around, and you can see how it loops in on itself when it does that. Okay, where B is greater than A. Okay, so maybe the, is it an epicycloid? No, no, no. An epicycloid is when a circle rolls around another circle, and that's like a spirograph. It must be the curate cycloid. Okay, yeah, so that's like the reflector on a bicycle wheel. So if you were to like use the kind of film that keeps, holds on to traces of things that are brighter, and you watch the bicycle wheel go by, that would be the path the reflector made as the bike rolls, which is kind of neat. And then, oh, I think I remember seeing another use of a cycloid. If I remember right, if your bicycle had square tires instead of round ones, if the road was made out of the right size cycloid, you would think you had round wheels on a flat road. And somebody actually built that bike once, which is kind of crazy. Oh, that's funny. Okay, so that's a curate cycloid. So that's when the radius of the point is smaller than the radius of the circle. And it's a similar drawing to what we get. Notice you just get a slightly different thing. The B is the radius of the object, where the A is the radius of the circle. That's bigger. So you get a slightly different shape there. And then let's look up epicycloid. That's kind of cute too. What's up? I was wondering how the graph will look if you had both a point outside and inside. Oh yeah, we could do that in Desmos at the same time. Okay, so what if we had a point outside and inside at the same time? All right, Desmos. So that would be something like, let's see, parentheses. The point, okay, so that'd be t minus like 1.5 times the sine of t, comma, 1 minus 1.5 times the cosine of t. So that would put the point on the outside and give us the prolate cycloid. Let's copy all of that and go to 2 pi. Actually, we probably should give it a little more room than that. Let's go to 4 pi so we can see that loop. Okay, so there's that loop there. And then here, let's see, we want it to be on the inside, so maybe we'll go like 0.75. Oops, wrong spot. And then go to 4 pi. 4 pi. Okay, so there's the two of them together. Interesting. All right, so we're going to take a look at, let's see. Yeah, it turns out that's not too bad. Well, no, areas are tough. And it turns out, let's do area next, then we'll do arc length next time. All right, so area. And can you see we're going to need this again when we do arc length? Because arc length involves, yeah, so all arc length is, if you integrate the speed, you get the arc length. That's it, yeah. And because of the squares, nothing weird happens. Weird stuff does happen in areas though, because think about rectangular areas. To find the area, we would usually integrate from some number to some other number of f of x dx, right? But here we have a problem. The problem is that both x and y are functions of another variable. So dx dt is actually something that has to do with the chain rule, because, right, x equals some other function of t. So if you think about dx dt, it's g prime of t. And if you think about the differential form of that, dx is actually a wee bit more complicated. It's g prime of t dt. So we have that extra complication that's going to go on in here. So what we'll have is, let's suppose instead of f of x, we have y is some function of t, and x is some other function of t. Then the parametric area going off that guy up there, definitely need rectangles. Rectangles have to have a height. Y is always the height. So I'm definitely going to have my f of t there. But my width not only depends on x, but it depends on t. So the width of my rectangles is always going to be g prime of t dt, as t goes from some number a to some number b. So that's parametric area, just a wee bit more complicated. What are the complications we had with area in rectangular functions? Well, if the y values got below the axis, we got negative areas. And if we were looking for total area, we'd have to be careful not to cancel things out. So here we have to be careful about not only if the y values are less than 0. So for area, we want f of t to be greater than 0. Doesn't have to be, but we also want g prime of t to be greater than 0. Otherwise, if it's negative, it means the curve just turned back on itself. Okay, positive x, if g prime of t is positive, that means we're heading in that direction. If g prime is negative, it means we're heading in that direction. And so if we try to integrate through a curve that does that, we just calculated this area right to there, then it goes negative, so then we start subtracting all of this stuff there, and then shit gets crazy. Okay, so you have to be super careful. You have to take a look at both f and g prime when you're taking an area. So what we do to be safe is we say, well, that's too restrictive. We really can't do that. So what we have to do is do that, which means you have to check the sign of both the y value and the derivative of x. Okay. So let's, and actually I changed my mind. I don't want to do the cycloid right now. I want to do the ellipse. Let's consider an ellipse. That's 2 L's up there, believe it or not. And ellipses in polar are parametric are pretty straightforward. Let's suppose my ellipse is centered at the origin, and we had A out that way, negative A out that way, B out this way, and negative B over that way right there. The rectangular version of this would be x squared over a squared plus y squared over b squared equals 1. We have the wonderful relationship that the cosine of t squared plus the sine of t squared is equal to 1, right? And so to get an ellipse in parametric form, all you do is say, oh, wait a minute. Hey, I got this cosine of t thing that's squared, and we've got this x over a thing that's squared. We got this sine thing that's squared, and we have this y over b thing that's squared, and they both equal 1. So let's just make that relationship. So we just say, okay, let x over a equal the cosine of t, which means x would have to be a times the cosine of t. And y over b gets to be the sine of t. So y gets to be b times the sine of t. And for this example, let's let a be 5 and B, B3. What's that? Oh, we're out of time. You're right. Okay. Well, tomorrow we will find this. But before I leave you, just a note. In the sign is going to be positive from 0 to pi. So as I revolve around, that's from 0 to pi. So I can get the whole top half. The x prime, though, what's x prime here? It's going to be equal to negative a sine of t. And the problem here is that that sucker's negative the whole time from 0 to pi, which makes the absolute value supercritical. Okay, and so we're going to end up with that negative sign. Absolute value is going to crush it, and then we could double the derivative from 0 for t to t equals pi, which will put us over there. Okay. But we got to consider the absolute value, because otherwise that becomes a problem. We end up a negative in answer, and that throws off the area. But we should be pretty safe doubling the absolute value from 0 to pi. So we'll finish that tomorrow. We'll also do arc length. So have fun with the homework. Let me know if you have any questions. I don't know if you noticed in the homework problems, there is a little link on the bottom of each problem that says ask your instructor or post this to the forum. So if you get stuck on anything, please post it somewhere so the rest of us can know what you get stuck on.